Hey, everybody. Welcome to our second apportionment episode of Social Justice Math. We have quite a few things to cover today, and this is going to be a very interesting one because it's going to show us some of the main difficulties that we have in applying mathematics to real life social situations. Sometimes those are not always as cut and dry as we'd like, and there's a lot of complex things going on with them. So even though we can use mathematics to kind of understand what's going on a little better, it doesn't always provide us the solution that we would like. So with that in mind, let's talk about apportionment in terms of what the Constitution actually says. So we talked about this a little bit in the last lesson, what apportionment meant and things like that. And obviously the big example of that for us in the US is the House of Representatives. And so this is how the House seats are apportioned according to the Constitution. So this is the original version from 1787. Representatives and direct taxes shall be apportioned among the several states according to respective numbers, which shall be determined by adding the whole number of free persons, including those bound for a service for a year of terms, so indentured servitude, and excluding Indians not taxed, 3/5 of all other persons. The actual enumeration shall be made within 3 years after the first meeting, and then every subsequent 10 years. So that's why we have a census every 10 years. Now, of course, it took us a little bit, about 80 years, but eventually we realized that that was a horrible thing. And we eventually decided to go to something a little more akin to this. So in Amendment 14, we say representatives shall be apportioned among the several states according to their respective numbers, counting the whole number of persons in each state. So getting rid of the severely problematic conditions of the other one and excluding Indians not taxed still. So this is our starting point, right? This is our basis for apportionment in this. So from a mathematical perspective, if we remember from last time what we looked at, we had a couple things that we had already covered with apportionment. First off, we had the quota rule, which said that no state should receive less seats than their lower quota and no more seats than their upper quota. So if we're given a population and a number of seats, then we can only apportion each state one of two consecutive integers. For example, they may get 4 or they may get 5 seats, but it's going to be between two consecutive integers there. And so we have the lower quota and the upper quota. We also have the standard quota, where we take our standard divisor, right, and use that to divide the population of the state. If you don't remember what standard divisor is, you might want to revisit the last video or look at the worksheet you did. And then, of course, our lower quota is just whatever the standard quota is rounded down. Upper quota is whatever it is rounded up. So that's going to kind of be the basis for the math side of things. So the method we're going to focus on, we covered, I think, 4 different ones last time. We're going to focus on Hamilton's method, which is where we find each state standard quota. And then what we're going to do is give out a number of seats equal to every state's lower quota, and then see how many seats we have left over. And then I'm going to give out those extra seats based on who has the highest fractional part in each state's standard quota. So if I look at the standard quotas and one is 13.8 and one is 3.2, I'm just going to look at those decimal places, the 0.8 and the 0.2, and I'm going to start handing out those surplus seats based on who has the highest decimal there. So I'll hand those out until I'm out of those extra seats, until I've hit the total number of seats I want, and then I am done. So here are a couple interesting examples that pop up when we use this method, which is a method that we have used in part for a decent chunk of the US history. So let's say, for example, we have a nation with 14 million people, and we're going to break it up into 3 states. So we have 10 seats, and we want to apportion these seats out based on these states' populations. So I'm going to let you practice this. This is very similar to what we did in the last lesson. I'll have the example fully worked out on our Canvas page if you're in my social justice class. So you can look at it there. But to just give you a quick idea of what goes down, we would have 14 million. That's our total population divided by the number of seats. That gives us our standard divisor, which should be about 1.4 million. And then we would take each of these populations for the states and divide that by our standard divisors. So 6 over 1.4, right? 6 million over 1.4 million, 6 over 1.4, and 2 over 1.4. And when we do that with the Hamilton method, what we end up with is that A should get 4 seats, B should get 4 seats, and C should get 2 seats, right? So they actually have the highest decimal place here. So they would be awarded that extra surplus seat. Okay. Well, let's say we run into a situation where the nation approves increasing the number of seats from 10 up to 11, right? So everything is the same. The populations are still the same. We still have 14 million people. We still have 3 states, but instead of 10 seats to give out, now we have 11. And again, I'll let you work this out on your own, or you can check the notes online. But to give you a quick idea of what happens, when we run it with these numbers, state A is going to get 5 seats, state B is going to get 5 seats, and state C is going to get 1 seat. Now, this is interesting because originally state C had 2 seats, right? And then we increased the number of seats, and all of a sudden they lost a seat. So they gave one of their seats away, and then the extra one also went to somebody else. Well, this leads us to something that actually happened in 1880. An increase in the number of seats from 299 to 300 resulted in Alabama losing a seat, right? So we call this the Alabama paradox, where we can increase the total number of seats we want to give out, but that can actually result in a state losing a seat. So this is a paradox because obviously it is counterintuitive that we would increase the number of seats we have to give out, but then somebody would end up losing seats instead of some people gaining some and some people staying the same. It seems weird that somebody would lose a seat in that scenario. Okay, well, let's go to another example. All right, let's say we have 3 clubs, Club X, Clubs Y, and Club Z, that are competing for SGA funding, and we're going to break up this funding similar to how we apportion seats. So let's say they have 11 total $100 bills, and they're just going to hand out those $100 bills in a way done by the Hamilton method. So the way we're going to apportion this is, instead of population here, we're going to look at the number of community service hours each club can complete in a 1-month period, right? So that's kind of acting as our population here, and our seats are these $100 bills. We're just going to assume that the SGA can't make change, and so they're going to have to hand these out as entire $100 bills. So if we break it down like this, Club X did 54 hours of community service, Club Y did 243, Club Z did 703. And so if we use a Hamilton method similar to what we did before, how would we break up these 11 $100 bills? Now, I'm going to let you figure this out on your own. Again, you can check online for the entire worked out solution, but I want you to practice this on your own and see if you can come up with it, because it's just the same method we used previously. Now, let's say that we run into a scenario where SGA actually forgets about their deadline, and so they decide, well, to be fair, let's go ahead and extend it for a week for everybody. And in this extra week, right, Club X gets 2 more hours, Club Y gets 12 more hours, and Club Z actually gets 86 more hours, so quite a few. In this new scenario, how would we apportion these 11 $100 bills? So again, I'm going to let you do this on your own to see if you can figure out what's going on here, but I'll give you the punchline. And that is what we call the population paradox. So Club X only had 2 extra hours, right, which was a 3.7% increase in their total community service hours. Club Y had 12 extra hours, which was a 4.9% increase. And so even though they got more hours and a higher percentage increase of hours, Y actually loses one of the $100 bills to X, right? So if the contest ends at the original deadline, Y gets an extra 100, but with this extra week, X actually sneaks one away, even though they did fewer community service hours and it was a fewer or a smaller percentage increase in their overall hours. So this gives us what we call the population paradox. State A can lose a seat to state B, even though state A's population increased at a higher rate. So we may have a scenario where we have 2 states, we have an influx of people into both of the states, a lot of people going to state A and some people going to state B. And even though a ton more people went to state A and their population increased at a higher rate, they actually end up losing a seat when we do our apportionment. Now, this is an illustration of how messy this gets, right? There is a mathematical theorem. So this is not just like an opinion. This is mathematical fact, which means in the system that we have set up with our Hamilton method, there is no way, right, that we can meet all three of these requirements. The quota rule holds, the Alabama paradox cannot occur, and the population paradox cannot occur. Now, we've already seen with the Hamilton method, we can hold the quota rule, but these two are going to fail. But here's the problem. Even if we go with something else, so one of the other four methods we covered, we can't get all three of these things, right? We cannot simultaneously meet all three of these requirements. Now, here's the fun part, and this is the part that is exciting about mathematics, is this works for any apportionment formula. That means anything that's been done, anything we could do. So there may be some ideas out there that somebody has 20, 30, 300 years in the future about how to apportion out seats. It still is not going to be able to satisfy all three of these. So we're already in quite a messy situation when it comes to that. Now, that gets a little messier when we think that not only do we need to figure out how to give these seats out, but we need to figure out where these districts are going to be that have these seats within each state. So obviously, gerrymandering is a big term. It has popped up a lot in recent history. But let's talk about where that term originally came from, right? So we have our gentleman here, Elbridge Gerry, uh, who lived from 1744, a little older than that, to 1814. Here is some of the fun things he did. He signed the Declaration of Independence. Then he refused to sign the Constitution. Then he was the vice president for 2 years. And he was also the governor and congressman of Massachusetts. So a lot of different things in there. Gerry lived quite an interesting life here. Now, when he actually was in charge of drawing the districts at one point, he was kind of shunned or shamed for drawing an oddly shaped district that ended up favoring him. So you can actually see the map down here. Now, obviously, he did not draw it like a dragon, but a political cartoon at the time saw this shape and decided it was very dragon-like. And dragon-like at the time, right, was compared to a salamander. So they decided to call this district the Salamander, and that portmanteau of Gerry and salamander, or gerrymander, kind of stuck after that to represent any weirdly drawn district that had a certain political advantage to it. So here's some more modern examples. This is in 2012. You can see this is North Carolina, and these are the way the districts are set up. So you have quite a lot of oddities in here. You have some that look decently okay, right? We have this yellow one and this blue one that has this weird part sticking out here. We have this dark blue one that looks kind of okay. We have this orange one over here, which is connected up by these islands. It's really like four distinct pieces, but they're all connected by the islands here. And then we have this one that you can hardly see, this pink one here in the middle, right? So this map has been called gerrymandered, both by people and by our justice system. So what we're going to do is we're going to try and understand a little more about what that term means, because it's something we can kind of understand intuitively, right? These districts are drawn in weird shapes for some sort of political advantage, right? You can see this red one even kind of sneaks around here, and this light orange one is in the middle of it. It just seems weird, right? So in that case, right, that's what we would call gerrymandered districts. But the real trick is figuring out when exactly something's gerrymandered and when something isn't. So this is the North Carolina 12th Congressional District. This is one of the worst ones. It's been up to the Supreme Court 5 separate times, I believe. It was originally drawn this way to try and give the African American population in the state voting power. So you can see it connects up a lot of different things that basically follows the interstate here. In fact, I think one of the congressmen at the time said if you drove down the interstate with both doors open, you would hit basically everybody in the district. So it goes right down the interstate, and several different groups have sued to get this redone. In 1992, it was part of a court case called Shaw versus Reno. And in that court case, it was eventually removed and then redrawn into something a little more normal, we'll say. So you can look up the history on that. It's actually quite fascinating how many different back and forths there have been. Like I said, I'm pretty sure 5 separate times it's gone to the Supreme Court in 5 different cases. So let's take a much more basic example, and let's see if we can figure out a little more intuitively what gerrymandering would look like. So let's say we have this region, right? And in this region, right, it's just going to be these 50 people. These 20 here are going to belong to the red party, and these 30 here are going to belong to the blue party, right? And let's just say this is how the housing arrangement is set up in this grid, right? And everybody lives on one of these blocks. So super nice and simple, right? Now, we need to divide this into 5 districts. So there are 5 seats that are going to come from this. So in an ideal world, how would we draw the districts to reflect party representation? The fact that 2/5 of the people belong to the red party, 3/5 belong to the blue party. But we could do something like this, right? Just draw a vertical line straight down, and then we would have these 2 districts on the left are red districts, and these 3 on the right are blue districts. So in this case, this would reflect that 60% of the districts are blue, along with 60% of the populace. 40% of the districts are red, along with 40% of the populace. So this is kind of a perfect match. Now, let's suppose the blue party here is in control of redistricting and they need to redraw these lines. So if they were given the option to do whatever they want, how do you think that they would draw the lines? So I'll give you a second to see if you can figure this out on your own before I click over. Okay, so did you come up with something like this, right? Where we draw with 2 rows in each one straight down. So in each district, we have 4 red voters and 6 blue voters. Now, this seems like, okay, well, 4 red, 6 blue, that's what we had last time, right? But not quite, because in this district, if everybody votes according to party lines, right, which for simplicity, we're going to assume is what's going to happen here, then they would draw this way so that the red members always get outvoted by the blue members. Okay, so that means in these districts, actually 5 of them would be blue and 0 would be red, which is not a reflection of what the populace was. Okay, so let's flip-flop this, right? Let's suppose the red party is in control now, and let's see how they might want to draw the districts to their advantage. It's a little harder to see here, but if you draw them this way, what you end up with is that this district here, and this district here, the ones that kind of hug this left side, those end up being red districts because we have 6 red members and 4 blue members, right? So in each one, the red is going to outvote the blue. And then we have some districts over here where it's 9 blue members and 1 red member. So those are certainly going to vote blue, right, instead of red because it's 9-1. But in this case, we have 2 blue districts and we have 3 total red districts, even though if we go back, 60% of the voters are blue, 40% are red. They've actually flip-flopped it. Now 60% of the districts are red and 40% are blue, right? So let's think for a second, right, now that we are at the end of this video, what makes these drawings unfair, right? What is the issue with these things? And that is something we're going to come back to in our next lesson. So for now, I want to thank you for your time. Thank you for watching, and I will see y'all in the next one.